This presentation is an introduction to electricity for physiology. We will cover current, resistance, conductance, and impedance, as well as the components associated with recording electrical activity from physiological mechanisms, such as EEG. Essentially, what we're recording when we're recording physiological electrical activity is the transport of mineral ions into and out of cells in the body. Our particular focus in this case will be on neurons in the brain and the cellular mechanisms that transport these mineral ions into and out of the cells, creating electrical charge differences. So, when we have a concentration of mineral ions with a negative charge in a particular area and a concentration of mineral ions with a positive charge in another area, that creates an electrical gradient or difference from positive to negative or negative to positive. And this difference results in an electrical field or electromagnetic field, which can be measured from the scalp surface. So we have intracellular, extracellular, intercellular concentrations of mineral ions of different charges, and that creates electrical gradients. And the mineral ions that we're talking about are minerals such as standard minerals in the body like sodium, potassium, calcium, chloride, magnesium, and others. And these are present in neural tissues in intracellular and extracellular fields and produce the electrical gradients that we measure from the scalp surface. As you can see from this slide, we have a typical pyramidal neuron with a soma or cell body. We have axons extending out from the cell body and dendrites, both in the apical dendrites and in the basal dendrites. And you can see that from this example there are multiple different representations of negative mineral ions located around the apical dendrites in this case, and positive mineral ions surrounding the cell body and the basal dendrites. This electrical difference creates an electrical charge gradient, as I was mentioning, and this creates a difference. Now, when we measure electrical activity, we measure essentially the difference between 2 points. So what we're looking at is a sensor placed in one location, and we're comparing the electrical charge gradient in that area compared to another electrode placed on another location. And so we're measuring the difference between those two locations. We're not actually measuring the electrical activity at one location alone. It is only the electrical activity that is the difference between the two locations. Those voltage differences can reflect static electrical fields, electrical current through a magnetic field, time-varying magnetic fields, or some combination of these three. What we see here then is two electrodes on the scalp surface, you could call them sensors as well, and reflecting these differences. So here we have a positive-negative distribution in this pyramidal neuron representation, and here we have a negative-positive distribution. And so the difference between those two locations produces the voltage difference. Now, voltage is measuring the potential difference between 2 points. And if you can visualize a hydraulic or fluid dynamics example of this in the example of a waterfall. So the greater the height of the waterfall, the stronger the the more amount of water is going to fall, and with greater velocity, as the difference between the top of the waterfall and the bottom of the waterfall becomes greater. So the greater difference between these two locations produces a higher voltage. Voltage is a measure of the difference in electrical charge between the two locations. Now, often we're measuring the electrical charge at this location against a reference potential, such as a system ground or a system reference, and we're measuring each of those locations against that system ground or system reference, rather than measuring these two against each other, although this is also done. So the EEG voltage represents the energy and charge gradient differences of positive and negative values between those two locations. Now, when we have this charge gradient difference, it causes a movement in those charged particles from negative to positive or positive to negative. Now, that flow of electrically charged particles is measured in amperes, and we're measuring the current. And if we go back to our waterfall analogy, depending on the amount of water in the available to the waterfall, if we have a higher waterfall, we're going to have more current flowing. And if we have more current flowing, we're going to have more particles, or water molecules in this example, flowing past a given point at a given period of time. So the greater the charge differential, which is the volts, the more current flows through, or can flow through that circuit. And so we're passing through a closed circuit or a series of closed circuits. And in this case, in terms of electron flow, we have a battery with a positive and negative pole, and we have negatively charged electrons traveling towards the positively charged end of the circuit because they're attracted to the positive end of the circuit. This flow of electrons is measured in amperes, as I mentioned, and so that's the second component of the electrical current measurement, or electrical circuit measurement, which is voltage in amperes. In electrically conducting solutions in the body, we have again mineral ions traveling from one place to another and developing gradient concentrations that are different from one point to another, causing an electrical charge difference and producing a electrical field or electromagnetic field. And again, we can measure this electromagnetic field from the scalp surface. And again, those charged particles are mineral ions such as sodium, potassium, calcium, chloride, magnesium, and so on. Now, this is a simple schematic showing an example of resistance. So we have the electrical current being represented here surrounding this pyramidal neuron, and this is the electrical field that is existing in the cortex, and measuring it from the scalp surface requires that we pick up this electrical field through a lot of different tissues and structures. Now, those structures resist the passage of this electrical field. If we put a sensor in the actual cortex near one of these pyramidal neurons, we'll see readings in the millivolt or thousands of a volt level. Once we get to the scalp surface, the readings have been attenuated or blocked by these structures: pia mater, the subarachnoid space, the arachnoid space, the dura mater, the skull, the scalp, and so on, resulting in an increase in resistance and a decrease in the amount of voltage that we can perceive from the scalp surface. So by the time it reaches this sensor on the scalp surface, we're reading in the microvolt level range, which is in the millionths of a volt. Now, multiple factors affect this attenuation or blocking of the signal to the scalp surface, and most of that we don't have any control of. So when we want to measure the flow of current, the amount of the voltage differential and the amount of resistance, we have a calculation that we can use called Ohm's law, which measures the voltage pushing or pulling the current through this circuit, and we have resistance trying to resist the flow of that current through this circuit, and this is represented by Ohm's triangle. Voltage equals intensity, which is amperes, times resistance. Resistance equals voltage divided by intensity, or amperes, and amperes, or intensity, represents voltage divided by resistance. So we can find any of these three factors as long as we know two of the other values. And so if you're thinking about the BCIA exam or the QEEGD exam, you're thinking in terms of how do you calculate this value when you have two values given on the test. And so just keep in mind that it's a simple triangular perspective where you have multiplication and division choices, and V is at the top and I and R are at the bottom of this triangle. If you just remember that V is at the top, then you by default I and R are going to be below that. Now, this is a little example of how this electrical activity is produced. These electrical differences are produced. Keep in mind that this is again a pyramidal neuron. Here's the axon, multiple axon branches. Here are the dendrites. We have excitatory inputs. These are coming from other neurons and producing excitatory postsynaptic potentials in this pyramidal neuron. Here's an inhibitory effect on this pyramidal neuron. And this is going to be a little bit of a brief description of that process.
The postsynaptic potentials that are caused by neurotransmitter chemicals can be either depolarizing, often but not always resulting in an excitatory postsynaptic potential, or EPSP, or hyperpolarizing, resulting in an inhibitory postsynaptic potential, or IPSP. Postsynaptic potentials generally move passively along the dendritic membrane, gradually becoming smaller as they spread. Therefore, the postsynaptic potentials from more distant synapses will decay more than PSPs from synapses closer to the integration zone at the axon hillock. The postsynaptic potentials produced at most synapses are usually well below the threshold for generating postsynaptic action potentials. How then can synapses transmit information if their postsynaptic potentials are subthreshold? Suppose that two excitatory endings are activated, causing local depolarizations of the cell body. Taken alone, neither would be sufficient to trigger an action potential, but when combined, the two depolarizations sum to depolarize the membrane in the hillock region to threshold. When inhibitory synapses are active, the membrane potential tends to be stabilized below threshold because they induce hyperpolarizations, or subthreshold depolarizations, that cannot reach threshold. These postsynaptic effects also spread passively, dissipating as they travel. Because some potentials excite and others inhibit the hillock, these effects partially cancel out each other. Thus, the net effect is the difference between the two. The neuron subtracts the IPSPs from the EPSPs. Postsynaptic effects that are not absolutely simultaneous can also be summed, because the postsynaptic potentials last a few milliseconds before fading away. The closer they are in time, the greater is the overlap, and the more complete is the summation, which in this case is called temporal summation. The summation of potentials originating from different physical locations across the cell body is called spatial summation. Only if the overall sum of all the potentials, both the EPSPs and IPSPs, is sufficient to depolarize the cell to threshold at the axon hillock, is an action potential triggered.
So essentially what this is saying is that there are a whole bunch of postsynaptic potentials, both excitatory and inhibitory, for every action potential that's created. Generally, for our purposes, this explains why the scalp surface EEG is primarily the result of the postsynaptic potentials. So, to explain in a little bit more detail what a postsynaptic potential is, we have an axon coming from another neuron, and it brings with it electrical charge that stimulates the terminal bouton at the end of the axon terminal, and that causes vesicles to open, allowing neurotransmitter substances to travel across the synapse and bond with the postsynaptic receptors on the dendrite or possibly the cell body. And that stimulates a change in this cell, and the change in this cell essentially is the opening or closing of either voltage gated ion channels or chemically gated ion channels, which again allows mineral ions to flow into or out of the cells, causing differences in the cell gradient, electrical gradient. So again, each of these actions, these postsynaptic potentials, are actually postsynaptic changes in the electrical gradient or the electrical potential of the cell, and that increases or decreases the charge gradient in the environment surrounding the cell, and that's what we're reading on the scalp surface. So all of these postsynaptic potentials produce those kinds of changes in the cell, and that's what we read on the scalp surface. So what we read on the scalp surface as EEG is the result of multiple influences affecting the excitatory and inhibitory postsynaptic potentials within these cells. Now, when we measure this activity on the scalp surface, we're actually measuring the voltage at any given moment, again between the active sensor and the system reference or ground. The term ground is a little bit misleading because it isn't actually attached to the ground, but it's usually called the system reference, which means it's the system reference that the other electrodes are compared to. So we're comparing the electrical gradient difference at moments in time, and the number of these measurements or samples is called the sample rate. For example, a typical EEG recording device currently in use would have a sample rate of approximately 200 or 256 samples per second or faster. More samples per second generally is better, and I'll show you an example of that in a bit. But for the purposes of this graph, what we have are samples or measurements plotted on a graph where we have 0 in the middle, we have positive values here, we have negative values here, and we have time across this axis, the x-axis here. So we're plotting these voltage measurements at each given point in time, and sometimes they're negative values because the charge gradient between the measurement sensor and the reference sensor is more positive or more negative in one direction or the other. So let's start with more positive at the active sensor, and then the active sensor becomes more positive in relation to the reference sensor, and then it becomes more negative in reference to the reference sensor, and so on. And the measurements reflect those electrical changes, those charge gradient changes. And we plot those measurements, and once we have enough plots, if we had 256 dots per second, we'd actually have a solid line, because that's a lot of dots. Here we can actually see the dots because there are many fewer than 256 dots in this 1 second period of time. But this is just for illustrative purposes only. And so each of these dots is a sample. We plot these dots, and essentially we end up with what looks like a solid line, and it looks like a wave. Now this wave is an artificial construct of the way we measure the EEG. The brain actually doesn't make waves. The neurons in the brain fire sometimes synchronously, sometimes asynchronously. When we plot all of that together, we end up with, on our computer generated plot, or even on our pen and ink generated plot, what appears to be a waveform. And so we talk about EEG waves like delta, theta, alpha, beta, and so on. And we've come to use those terms, and we think of the activity in the brain as being associated with waves. But again, these are constructs that allow us to visualize and discuss and compare EEG from one person to another and within the same person. But these are simply constructs of our way of plotting the data. Now when we do plot this data, we can see that the brain produces multiple different kinds of rhythms. And when we look at the raw signal, we see a composite of all of these. If we use filters, and we'll talk about filters in more detail later, when we filter the EEG and select out different segments of the EEG, for example, here we have 1 to 4 waves per second. Here we have 4 to 8 waves per second. We're only taking the data that falls within that 4 to 8 waves per second, usually labeled as hertz, sometimes also called cycles per second, or CPS. Here we have 8 to 12 waves per second, so here we have a 1 second period of time. If we were to count the peaks here, we should be within that 8 to 12 wave per second range. Here we're looking at 12 to 25 waves per second, and so on. We have labels for these. We call these delta waves, 1 to 4 hertz. We call these theta waves, 4 to 8 hertz, alpha, 8 to 12 hertz, beta, 12 to 25 hertz, gamma, above 25 hertz. However, these labels are somewhat fluid, and they differ depending on which publication you're reading and who you're talking to and what database you're using, and therefore they're a bit imprecise. And in some ways it would be more precise to use numerical terminology and actually call this a 1 to 4 hertz wave, or even a 3 to 5 hertz wave, or whatever the distinction would be, rather than using labeling terminology. Because, for example, the 4 to 8 hertz activity that you see is very locally specific. And so 4 to 8 hertz activity in the frontal midline of the scalp is going to represent different types of behaviors and patterns than the 4 to 8 hertz activity you might see in the temporal lobes or in the occipital areas. And so keep in mind that theta in one place is possibly a different animal than theta in another location. Now when we talk about electricity, we have a couple of terms that we have to become familiar with, partly because these questions will be on the test, but also because we need to understand how these terms affect how we measure the EEG. So two of the terms that we use quite frequently are impedance and resistance. Now we use these terms because we're measuring how much resistance there is in the scalp surface that blocks the passage of electrical activity into our sensors. And so we're concerned with reducing that resistance so we have the least amount of resistance possible, so we have a good quality connection to the scalp surface. Now we measure that in two different ways. The term impedance represents measuring that resistance using an alternating current. And typically it's a 10 hertz or 10 waves per second current that's introduced by the hardware, and it's introduced to the circuit. So we're actually running a 10 hertz electrical current, a very, very low ampere electrical current through this circuit to determine how much of a voltage drop we'll have between the beginning of it, where we know how much voltage we've generated on the initial end, and how much we measure when it comes to around to the end of the closed circuit. We can measure how much voltage we've lost, and with Ohm's law then we can determine the resistance. Remember, Ohm's law is voltage equals uh, um, amperes, or intensity, times resistance. And so if we know voltage and we know the amperes starting out, then we can divide the voltage by the amperes and we can come up with the amount of resistance. And so that's the calculation that's done in the software, of course. We don't actually do this ourselves. And so this impedance value is what we use generally to measure the resistance of the circuit elements to the passage of alternating current. We do this because we want to avoid polarizing the electrodes. If we were to use a direct current, which is what we use to measure resistance, we'd just be passing an electrical current only in one direction through this electrical circuit. And by passing the current through the circuit in only one direction, the circuit becomes accustomed to passing the current in one direction only, and it aligns itself. The electrons align themselves in that direction, and then they tend to be more resistive when we introduce an alternating current, which is what EEG activity tends to be. So we use impedance where we're already starting out with an alternating current, where we alternate the direction of the current going through, sometimes positive, sometimes negative, alternating every 10 times per second, 10 hertz alternating current signal. That keeps the circuit elements from polarizing or becoming aligned in one direction only. So that's the difference between impedance and resistance. Impedance is using an alternating current, resistance uses a direct current. Now, the factors that we have control of, as I mentioned earlier, we only have a minimal amount of control about the amount of resistance between the brain and the scalp surface. One of those areas that we can control is skin preparation, because we want to reduce the resistance by getting rid of dead skin cells and skin oils that might inhibit the passage of electrical activity. So we prepare the skin, and in the past we would use fairly aggressive means, including poking a hole in the skin with a needle to get an adequate signal, but that's not necessary anymore, and in fact is counterproductive in terms of infection control, which we'll talk about at another time. So in this case, skin preparation is done simply using an alcohol swab and rubbing the skin surface somewhat vigorously, but not enough to break the skin, to remove any loose dead skin cells, surface skin cells, and oils, so that we have a nice clean and oil-free surface upon which to place our sensor and our sensor paste. The other choices that we have about this process is paste and sensor application. We need a good layer of paste, which is a conductive medium between the sensor and the scalp, because the sensors themselves don't provide a very good conductive medium. It's the high chloride content of the conductive medium, the sensor paste, that allows for this mineral ion current flow to occur between the scalp surface and the sensor. It also helps maintain the sensor stability because the paste is fairly dense and sticky, and it provides a substance that the sensor can be embedded within, so that it maintains that contact between the sensor and the skin. The other factor that we have control of is the quality of the sensors and the connecting wires. We want to make sure that we don't have any breaks or disruption in the sensor surface. The sensor surface is usually conductive, and sometimes the substrate or underlying structure may be less conductive. For example, quite often there are gold-plated electrodes where the plating is over silver, and if the plating wears through to the silver, then you have, first of all, two different types of metal, which causes problems by itself, but also you have a decrease in the conductivity because gold is more conductive than silver. You can also have breaks in the wires or worn sensor surfaces, which increases the resistance, so it's important to have good quality attachments to your client's scalp. Now, the other thing that we're concerned about is our environmental electromagnetic field issues that exist in every location, because every location that has electrical wiring has electrical fields. These are electromagnetic fields caused by the passage of current through wires. And the passage of current through wires produces electromagnetic fields. Depending on the intensity of that current in that circuit, it can produce an electrical field that it can extend out into the room by several feet. So it's something to pay attention to. For example, if you're in an office and possibly on the other side of your office wall someone has a large refrigerator, the compressor in a refrigerator produces a very large electrical field, and depending on the materials that your office is constructed of, that electrical field can extend into your office and affect the EEG that you're recording, because that electrical field oscillating at 60 times per second, because that's the electrical signal that goes through the wiring in your walls, the AC current is 60 cycles per second in North America, 50 cycles per second in most of the rest of the world. Certainly in Europe and Asia, they use 50 cycles per second. In the US and North America, we use 60 cycles per second. So we call that 60 hertz artifact because it's oscillating at 60 times per second, and we'll see that 60 cycle wave showing up in our EEG recording because of this electromagnetic field effect. There are a couple of things you can do to avoid that. First of all, you can check your environment and see if you have a noisy electrical environment. You can make sure that everything is well grounded in your environment, that the wiring is done correctly, and even just check the location where you're putting your client's chair and determine if it's a noisy location in your office, and possibly choose a different location. One of the ways you can do this is by hooking yourself up or a volunteer and have them walk around the room with the sensors attached. And because the Nexus amplifiers are Bluetooth amplifiers, you can have the client just carry the amplifier around and stand close to the walls in various locations and determine the quietest location, and if possible place your client chair in that location. So this is the end of this presentation. You may review this at your leisure at any time.